Welcome to The Explainer. Today, we're going to demystify one of the biggest challenges in AI. How do you take a massive general-purpose AI model and teach it to do a really specific job without, needing a supercomputer and a giant budget?
Right. Let's just dive straight in. So we have these incredible foundation models, right? They know so much about the world, but getting them to specialize in your world, whether that's understanding complex legal documents or medical charts, or even just your company's unique internal slang, that's a whole other ballgame.
But here's the cool part. What if I told you the solution is actually way more elegant and accessible than you'd imagine? There are these new techniques that are totally changing who gets to build custom AI, taking it out of just the massive data centers and putting it into the hands of pretty much anyone with a decent computer.
Okay, so to really appreciate just how cool the solution is, we first have to get a handle on the problem itself. And that problem revolves around something called fine-tuning, which is basically the process of adapting these huge, large language models. So, in the past, you kind of had two options, and they were at completely opposite ends of the spectrum. On one side, you've got full fine-tuning. This is the brute force method. You retrain every single parameter in the model on your new data. It gives you amazing customization for sure, but the cost and the computing power you need are just astronomical. On the other side, you've got prompt engineering. This is where you just get really, really good at crafting the questions you ask the AI. It's cheap, it's fast, but let's be honest, the level of real customization you can get is pretty limited.
And the problems with full fine-tuning are bigger than just the insane cost. There's this very real risk of something called catastrophic forgetting. That's where the model, in the process of learning your new specific thing, actually forgets some of the super important general knowledge it started with. Not good. Plus, you end up creating a whole new gigantic model for every single task. It's just not efficient or scalable at all.
So, this exact set of problems, this is what led to a really brilliant breakthrough idea, a whole family of techniques that we now call parameter-efficient fine-tuning, or you'll usually hear it called PEFT for short.
And the entire philosophy behind PEFT, the core idea, can be boiled down to this one simple but super powerful mantra. Instead of changing everything, you just change what's absolutely necessary.
So what this means is, instead of trying to update hundreds of millions or even billions of parameters, PEFT methods are smart. They strategically target and update only a tiny, tiny fraction of them. And this gives you the best of both worlds. You get that deep customization you want, but without the crippling cost and resources. And that brings us to probably the most popular and widely used PEFT method out there today, LoRA. That stands for low-rank adaptation. I love this analogy because it's just perfect. The big, powerful, pre-trained model, that's your professional camera body. It's already great at what it does. LoRA is like a small, lightweight lens that you just snap on for a specific job, like taking portraits or shooting wildlife. You get brand new capabilities without ever having to touch the core machinery of the camera itself. And the way it works is actually ingeniously simple. Step 1, you freeze all the weights of the original model. You lock them down. Nothing in there is going to be changed. Step 2, you inject these small new layers of trainable parameters, these are the LoRA adapters, right into the model's architecture. And then step 3, when you start training on your new data, you only update these tiny new adapters. The huge original model just stays untouched. The impact of this is, well, it's just staggering. Look at this example. With LoRA, we can cut the number of parameters we actually need to train for a new task by over 99% in some cases. It's just a massive leap forward in efficiency. And this incredible efficiency leads to all these amazing benefits. Because you're training so few parameters, the memory and hardware you need just plummets. These adapters are tiny and modular, right? So you can have one for legal text, another for medical data, and just swap them in and out as you need them. And because that original model is frozen, you completely sidestep that whole catastrophic forgetting problem. It really is a game changer. Okay, so LoRA is amazing, but what if we could push this even further? What if we could make the whole process even more efficient? Well, that is exactly what QLoRA is all about. So, QLoRA takes that next huge leap in efficiency by basically compressing the giant base model itself. It's a lot like how you compress a massive high-res photo into a much smaller JPEG file. And the core idea that makes this possible is a process called quantization. So what is quantization? Well, it's all about making the numbers that make up the AI's brain a lot simpler. Instead of using these super precise 32-bit floating point numbers, it converts them into much smaller, lower resolution 4-bit integers.
This move alone dramatically shrinks the memory footprint of the base model, and that's before we even start training anything.
Let me make that more concrete. So instead of storing a really complex number like 0.2121345678, a 4-bit system just finds the closest value out of only 16 possible options, and then it just stores a reference to that position. So in this case, it's position 10. It's an approximation, yeah, but it's a very, very clever and efficient one.
And QLoRA is really a combination of this 4-bit quantization plus a couple other really smart tricks. It uses something called double quantization, which basically compresses the compression data itself, pretty meta, and it uses paged optimizers to cleverly manage memory on your GPU to prevent it from running out and crashing. It's a whole suite of optimizations all working together.
Okay, we've gone through a lot of the technical stuff. But what does all of this innovation actually deliver? What does this mean in the real world?
Well, the numbers really do speak for themselves. If you take a medium-sized model, say 345 million parameters, full fine-tuning means you're training all 345 million of them. With LoRA, you might only need to train 12 million. That's about 3.5% of the total. I mean, that is a colossal difference.
And of course, that huge reduction translates directly into hardware savings. Full fine-tuning might require a beefy professional GPU with 16 gigs of VRAM or more. But with LoRA, and especially with QLoRA, you can often get the same job done on a regular consumer-grade gaming GPU with just a tiny fraction of that memory.
And this is the ultimate takeaway, the most crucial point. Methods like LoRA and QLoRA, they aren't just some minor tweak. They represent a fundamental shift. They deliver these massive efficiency gains. We're talking reducing memory usage by over 70%, all while achieving performance that is right up there with the old expensive methods.
What this really does is it democratizes access to powerful AI customization. It's no longer a game that only massive corporations can play. And that leaves all of us with a really fascinating question to think about. When anyone with a good idea and a decent laptop can build their own specialized AI, what incredible new things are they going to build next?